Hi everyone, and welcome to Eric's Electronics Workbench. So I recently purchased this electronic load. It's also known as a Dynaload. It's made by Transistor Devices Inc, or TDI, and it's their model DLP 5060-1000A. Now in the advertisement for this instrument, there were two things that I noticed. First of all was the cosmetic condition. So the instrument looks outstanding for its age. It's about 40 years old, maybe even older than that, and it really does look quite nice. The front panel's in great condition, the paint's good, the graphics look very nice. There's no damage to the meters, the glass isn't scratched, anything like that. And the back panel looks very nice as well. Now, if we take a look at the bottom, you can see that there are 4 rubber feet are missing, so someone has removed those. But that's a minor thing. I can easily replace those. I probably have them on hand, and if not, I could certainly order them. It's been rack mounted. You can see there's some marks right here where the screws went into the rack on that ear and also on the ear over there. Now the second thing that I noticed, these instruments are quite expensive, and this one was listed for way under half of what they normally go for. So the seller was listing it as untested as is and no returns. Now I was suspicious that maybe the seller knew a little bit more about this instrument and maybe thought that it had a problem and didn't want to disclose that, so it was just being sold as is. But the price was too good to pass up, so I went ahead and took a chance, and here it is on the bench. Now I haven't powered it up. This does run on 120 volts AC for the electronics, of course, inside and the cooling fans. But I did take a measurement on the input over there on the binding posts, and I found a problem right away. So we'll take a look at that in just a second. And the reason I went straight to measuring on those binding posts is because in a Dynaload like this, usually if there's a failure, it's going to be on the power handling circuitry. That's usually what gets overheated or overloaded in some way, and the faults tend to turn up in those parts of the circuit. So taking a measurement on the input terminals before even connecting it to anything is a very good idea. Now, I don't know the rest of the electronics in here. Maybe it's way out of calibration or has other problems. Who knows? We'll get into all of that as we do the troubleshooting. Now, before I do any testing, let me just zoom in on the front panel real quick, and I'll just show you the controls and indicators just so you have a quick overview of the instrument. So, of course, the AC line switch right here to turn the main power on. There's a current sample right here, so this is just an output from the current shunt that's inside the instrument. And there's a sync output right here for the pulse modulation, and this is to trigger an oscilloscope, and you can monitor the current sample pulses that way as well. If it's a constant load where there's no pulses, and this is of course just a constant voltage coming out of the current sample. Voltmeter and ammeter, of course the range switches for each meter. And the main operating modes right here. So you have the 1 amp per volt, 10 amps per volt. So that's the constant resistance mode. 0 to 10 amps and 0 to 60 amps are the constant current modes. 0 to 50 volts is, this acts like a power zener in that case. So let's say you set this to 10 volts. Up to 10 volts, it doesn't draw any current, and then at 10 volts and above, it will draw current to try and hold the input at 10 volts or whatever voltage you happen to set this at. So it can draw very heavy current. If you're not careful, you typically need to limit that current in some way. So again, it acts like basically a zener diode. External modulation, there's a connection on the back panel to externally modulate. There's a pulse generator built in, and that's the controls right here. This inner knob and the outer knob has the amplitude and the frequency controls. And then there's a short circuit, so if you press this button, you have to be careful because it will put a short right across the input terminals. It's useful for testing power supplies or other devices that you want to simulate a short circuit condition, but if you're not prepared for that, you could certainly draw excessive current. Now there's a circuit breaker right here, and this is rated up to 60 amps input. I think the breaker trips 65 amps or something like that. It's a little bit over the 60 amp rating, but if your source can't supply 60 amps, then this short will just hold the current extremely high, and you need to be aware of that. You might want to externally fuse between this and your device that you're testing. And right here, I don't think I mentioned, this is the coarse and fine control for the main load control, LEDs for the operating modes. So very straightforward, very useful controls and functions for a Dynaload, or an electronic load if you like. So let me turn it around on the back panel as well. You can just take a quick look here. So this terminal board right here says external modulation, so that's how you can externally modulate the instrument. And there's a positive 6-volt output for convenience. That output is it doesn't have to be used, but it gives you a 6-volt because 0 to 6 volts is the full scale input on the modulation. So if you don't have a 6 volts handy, then you can use this output right here. Cooling fans, so the air goes in on these vents right here and comes out under here on the heatsink. Positive and negative inputs for the main load. These are just in parallel. So the inputs on the front binding post, I think, are limited to about 10 amps. So if you want to go up to the full 60 amp rating, then you need to use the binding post back on the rear panel here. Fuse for the AC line, and of course the main AC input. Now it is interesting to note that this is a more modern style AC line input. That's actually technically known as an IEC 320 C14. Everybody just calls them a C14, or it looks like a computer type plug and receptacle arrangement. So the mating plug is a C13 plug. But I think this is a more newer, more modern version of this Dynaload, because earlier models didn't use this connector, and I'll put up on the screen right now what the earlier models used. And I actually have a Dynaload TDI DLP 130-15750A. So that's a very similar model to this. It has a higher voltage rating and a little bit lower wattage rating, and the current is substantially lower, but it looks identical to this model. In many ways, it's really just the electrical readings that are different. And you can see in that photo on the screen that the AC input is a very old style looking input. So this looks more modern. I think this is probably a newer version in production. So I'm curious to see what the date might be of production, because there are no dates on the outside. There's probably date codes on the components inside. We'll have to look for that. The schematics that I have for this instrument are dated around 71 to 73 for a lot of the schematics, but I think this is probably newer than that. All right, so let's go back to the front panel here. Let me get this turned back around here. And zoom this back out a little bit here, and I'm going to grab my ohm meter, and I'll show you the test that I did. So again, I have not powered this up. I haven't even opened it up yet. And the only thing I did was to measure this across the input here. I'm going to grab the ohm meter. Sit there. So I think you can see the display there. Yep, that's okay. So of course, if I take the leads and just touch them together, the display goes to all zeros. So if I turn the circuit breaker on and just go across the input, so the red is positive, white is negative, and the green is chassis ground. So you don't normally use the green terminal for the load. It's just a convenience to chassis ground. So if I go like this and go across the main terminals, you can see there's an absolute dead short circuit right there. That's definitely a problem. And if I go to the diode test, so on diode test, if I touch the leads again, it goes to zeros. If you're testing a diode, you know, you'd see 0.7 or 0.5 or some value like that for the voltage drop. But again, if I go across the terminals like so, you can see right there, absolute dead short circuit. And if I reverse the polarity, like so, it doesn't matter, still short circuit. So something went very wrong inside this Dynaload. There's definitely a problem with it. So let's get the top cover removed and take a look inside, start the troubleshooting. So when you look at a TDI Dynaload, you can always tell its electrical ratings by the model number. So when you look at DLP and then 50, 60, 1000A, so the 50 is 50 volt maximum, 60 means 60 amps maximum, and 1000 means 1000 watts of dissipation. So like I mentioned, the other Dynaload that I have that's a 130-15750A, that's 130 volt maximum, 15 amps, and 750 watts of dissipation. So it's always easy to tell what the actual ratings are. However, you can't do all of these at one time. For example, 60 amps at 16.66 volts is 1000 watts. So that's the absolute maximum voltage that you could have at 60 amps, because again, 16.66 volts, 60 amps, that's 1000 watts. So let's say you were putting 5 volts into here and drawing 60 amps, that's only 300 watts, but you can't go higher than 60 amps to go up to, say, 1000 watts, because you're at that 60 amp limit. And then as a final example, let's just say that you were at 50 volts input on here. You could draw up to 20 amps, and 50 volts at 20 amps is 1000 watts. So there's always some combination of these absolute maximum ratings that you can go up to. Now these Dynaloads have protection built in as well. So there's an over voltage protection, reverse polarity protection, and over power protection. So they're very well protected, and they're pretty robust and pretty ruggedly built. So again, to see this one with a dead short circuit probably means something overheated. That's going to be my guess, but we'll find out as soon as we start the troubleshooting here and take some measurements and look at the internal components. But again, they're definitely built to take, I shouldn't say abuse, but mistakes that you might make. Again, you're not going to be able to draw substantially over 1000 watts. It just simply will limit the current and so forth. So they're definitely well designed. All right, so let me grab a screwdriver here. I think these are Phillips screws. Yep, they are. Get this turned on the side here a little bit. You can see this here. So the case on these Dynaloads has a slot on these screws, so you actually don't have to run the screw all the way out. You just back them out a little bit, and then the top case will lift off, and then there's a cover on the bottom as well. So turn this around here. And let's get these three loosened up here. All right. There we go. All right, so, yep, that right away, that looks very similar to the other Dynaload that I have. That other 130-15 750A. So, what I might do, actually, I think you could see this better. You want to have it on the side here, or maybe turn it upwards here. That actually might work. A little bit better view looking inside there. I'm going to zoom in like so. Just take a quick look around in here. So as I'm looking in here, I'm not seeing anything that's jumping out as complete, disaster as far as complete melted down charcoal chunk or something like that going on. It actually looks really clean in here. They do a beautiful job building these. All the wiring is loomed and everything. Looks very nice. So the main circuit board up here. Right away, I'm noticing that all the calibration points look like they have the factory seal on them, this sort of a brown colored, let me zoom in a little closer here. You can see that here. So see this brown colored like a paint or whatever, it was to make these, so that they didn't vibrate or change in position. So it looks like nobody's been in here with a screwdriver making, changes and adjustments, so that's really nice to see. So all the components on the board look good. I don't see anything that looks overheated on this circuit board. Now, this board is not the main load control, of course. This is just the control to drive the main pass elements. So this is all low current up here. But yeah, it looks really good. The main power transformer itself doesn't look overheated or anything going on. The capacitors don't look bulged. Now I'm inclined to change these capacitors. We'll do the initial troubleshooting, and assuming if one of these has failed, maybe that's going to be an issue right away. We'll find out, take some measurements across those. But even if they're working, given the age, these look original. I think it would be a good idea to change those out. So can get to that after we do the troubleshooting. But yeah, no, it's looking very reasonable in here. No serious problems, and actually it's amazingly dust and lint free. So it must have been in a pretty good, clean environment. Kind of the midpoint right here. So this is the current shunt right here. All those resistors are in parallel. So very low value resistors, plus they're paralleled. So there's a very low resistance across from these 2 points. These wires going off here, going to the amp meter. But they don't look overheated. So I'm not seeing any problems there. And you can see how they've routed around. There's a lot of these bus wires that are in here. And then all the pass elements that are on the bottom, there's many of those transistors, and it routes the lines all around to all the pass elements. So right here, let's see if it's on the camera. Let me move this up just a little bit here. Pardon the camera movement, but there's an SCR right here, and this is the overvoltage SCR. So if this goes, I think about 55 volts on this model, if it goes to that point, this SCR will fire and it will just crowbar the input. So the idea is that if you have enough current, you'll trip the main circuit breaker, but it will certainly crowbar the input and protect all the components inside of here. So this SCR could be faulty. That's a possibility. If that SCR is shorted, you will see a short across the input terminals, so we need to keep that in mind. And let me just move this down. Well, you can see right here. So this is the main input right here from those rear panel input terminals. You can see the main wires are all attached on here. And right here is a diode. I don't know if you can quite see it. Let me just turn just a little bit here. So see that diode right there? So that diode, the reason it doesn't need much of a heat sink is because this is just the reverse polarity protection diode. So this is just across the input, and if the input has a reverse polarity, this will conduct, otherwise it's reverse biased, it doesn't do anything. Again, if this diode has failed, you're going to see a short across the input terminal, so it is possible that that diode is giving us a problem. And that'd be easy enough to test. You could just unbolt it and take it out of the circuit that way and see if that makes a difference, so something else to keep in mind. Take a look down here a little bit further. So this relay, sometimes it's called a contactor. This is what provides that short across the input when the short circuit button is pressed. So just a brute force way, just basically, you know, crowbars out those inputs. The manual makes a mention that you can actually weld the terminals in here if you're not careful. If you have a high, large capacitance in the power supply or the device that you're testing, you can arc the terminals in here and cause a problem. You have to be careful of that. But yeah, no, it looks all right. I mean, the wiring looks great. It's all high temperature wiring that they used in here. Insulation holds up really well over the years. But I'm not seeing anything from this side, so I think we're going to have to start in on some troubleshooting. Let me take the bottom panel off too, and we'll look at all the series pass elements. Now I am noticing something that looks different than my other Dynaload over here. Let me zoom in a little bit closer in this bottom corner right here. Check this circuit board out. So it looks like an entire circuit board right here, this transformer, so they must be running maybe 120 volts over here to power it. Yeah, there's a little bridge rectifier there, some filter capacitors. This looks like a little power supply. And I can see right away there's two wires right here that go to this back terminal board, so that input for the external modulation they're bringing over to this board. And actually, I am noticing a very interesting integrated circuit. If you can see that right there, that Burr-Brown integrated circuit. So that's a 3650 MG. We can actually do a whole video just on that integrated circuit. That's an interesting circuit. That's an isolation amplifier. It's actually, they're optically coupled linear isolation amplifiers. So it's interesting that they use that in there. I think these chips are rated up to 5,000 volts for 10 seconds of isolation from one side to the other, you know, across that optical isolation. So yeah, they're a very interesting chip. So I'll go ahead and toss up the data sheet. You can pause the video if you're interested to see a little bit about this integrated circuit. Again, you could pretty much basically do an entire video on that circuit, this integrated circuit chip. Yeah. So they must be using that on the input here just to isolate for the external modulation. My other Dynaload, I don't believe it has this. I didn't see this in the other model. So they were just taking this input and routing it to the main control circuit board. So they must have decided that they needed some better isolation. So interesting that they used that chip. All right, so let me zoom back out here. So let's take a look at the bottom here. I'm going to flip this around. So actually maybe just keep it turned long ways like so. Pardon all the camera movement here. It's kind of awkward to get everything in the shot at one time. So let me go ahead and pull this bottom cover off. So there's a number of screws right here. So let's get started on that. So to run these all the way out, unlike the side screws where they were slotted. So all the series pass transistors are under here, and I think, if I recall, there's 20 or 22 transistors under here. There's quite a few. And I think they use 2 of them as driver transistors, and then the rest are the pass elements. So you basically can think of these transistors as acting like variable resistors. And they're just taking the input and dissipating the power, you know, as heat into the heat sink. All right, so cover comes off. Clean looking cover. Don't see any lint or excessive dust there, so that's always nice to see. Oh wow, yeah, that looks really nice. Yeah, tip this up on its side here. Wow, that is really clean. There was the other Dynaload when I received that model. I had a lot of cleanup to do inside it. It worked when I got it, but it had dust and lint, you know, everywhere under here. And this one is extremely clean. This must have been in a really nice environment. Move this up here and you can see. So check out all those transistors. So this right here is the other side of that SCR for the overvoltage protection. So we got 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh, one's been changed there. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yep. So what are they using here? This one's actually looks different. These all look, oh, yeah, they're 2N3055s made by RCA, and the date code is 86. So it is a newer model. Very interesting. So I'll get you zoomed in a little closer here and you can see they all have a blue dot on them. And let me go up here. So this one right here looks like a repair has been done because it's also a 2N3055. It says TSL, 94 date code. So that one, you know, the original failed and this was replaced. All the others, I'm looking here, they all have blue dots on them. So the blue dot, I'm imagining, was probably, they were matched. Probably the gain was matched on them. And that's a good idea, that they would all be matched, you know, relatively close. Now they all have emitter resistors on them. I noticed that on the other side. So the emitter resistors help, you know, all the transistors to share the load correctly and evenly. But again, you do want them, you know, fairly well matched. So interesting that this one's already been changed. I wonder if this one failed again. So I'm gonna have to think about how we want to go about testing this now. I mean, one option is, also, I don't know if you noticed, these were in sockets, so they're very easy to remove. You could remove all of them and test them, but that's, you know, that's a lot of work to take all the transistors off. I actually have a different idea for testing here. A little bit of a brute force method, but I think it might work here. It's worth a try. I'm going to zoom back out again. I just want to show you one other thing right here. So I mentioned that the airflow goes in those vents on the back. So the way that the cooling system on this works, you can see these slots through the heatsink. You know, you can basically look through, see the slot right here, and you know, all the other places, those long slots. So some of the air, it's blown in on the top of the instrument and it comes through these slots, but remember this was covered, and then the air goes out the back. And then there's this long open area up here, so any air that doesn't get through these slots can come through in this area here and then makes a U-turn and goes through this direction here. Knowing that, it's really important on these not to overload them when the covers are off. You can briefly run them, of course, with some load, but these heat sinks will get warm pretty quick, especially if you're drawing, you know, several hundred watts of power. And there's absolutely no cooling when it's open like this, so you could definitely cause an overheat, you know, condition and damage things with the covers removed. So keep that in mind if you're working on something like this. And as always, if you're working on an instrument like this, you're doing so at your own risk. Just take care and be safe and know the dangers around, you know, the line voltage and things like that in the instrument. So again, if you're working on something like this, you're absolutely doing so at your own risk. Always keep that in mind. So my idea for testing is, let me hook this up to a power supply and I will slowly increase the voltage. It won't be very much because we have a dead short, but let's let some current flow through this. Even though there's a short circuit, I'm not even going to turn on the AC line. And let's see if a component heats up. And wherever the short circuit is, I'm suspecting that we're going to detect some heat. So a little bit of a kind of a brute force method, but you know, the component's already damaged, so you know, let's see what happens. And I won't go so high as to cause further damage. I don't want to damage, you know, any resistors, current shunt, something like that. But I'll use one of my variable voltage power supplies, and let's maybe say, you know, 10 amps or something like that. Let that run through there and see if a transistor heats up, or if we can detect, you know, if the SCR is shorted, maybe it'll start to warm up, something like that. So let me grab some test leads here. So I will go over to this power supply here. Pardon the camera movement. Okay, so that power supply that you see over there, that Sorensen SRL 40-25, we'll go ahead and use that power supply. And I've got these leads right here. All right, so I'm just going to plug these test leads in here like so. That. And we'll go around on the other side here. And I'm just going to clip them to the back of the Dynaload. So again, pardon the camera movement over here, but So this is the negative is right there, positive right there. Okay. All right, so now I'm going to go ahead and turn the voltage up on this power supply just a little bit. And first thing I need to do is get the circuit breaker turned on up here. There we go. Oh yeah, look at that. So again, pardon all the camera movement here. Can't really show everything in one shot, but take a look over here. So this is the amp meter over on this side right here. Watch what happens when I increase the voltage. There's 10 amps right there, and there's almost no voltage because we have a dead short. So I'll just leave that at the 10 amps right there. Pardon the camera movement again. So with 10 amps flowing in here, oh, that one feels a little warm. Uh-huh, yep. This one here is feeling warm. This transistor right here. All the others are just as cold as the heatsink feels. Oh yeah, that one, this one's warming up. Now this replaced transistor up here is not, so I think it's okay. Thinking I might want to replace that or take a closer look though, just because it's already been messed with. But yeah, this one here is getting warm. Yep, I think that's the fault right there. I'm going to turn that down again. So I've shut the power supply back down. You know, I can smell something a little bit on the, kind of smells that warm, kind of old electronic smell. So I'm wondering if maybe resistor or something in here. Don't really feel anything. The current shunts are mildly warm. Really not much going on there. Nothing major. Oh yeah, so this, I'm going to turn this here. There's an emitter resistor on that same transistor. I know this is kind of difficult to see because it's dark down inside the unit here. Let me grab a flashlight here. So that's the socket for the transistor that is defective right up in there, and there's an emitter resistor that's soldered, you know, to the emitter lead right there, or emitter terminal on the transistor socket. And when I put my hand right in here, I can feel pretty good warmth on that resistor. And just by comparison, there's some others down here. They're stone cold. Yeah, but so there's definitely current flowing through that resistor. So that pretty much confirms that there's a problem, something is going on with that transistor. So let me go ahead and get that transistor removed, and we'll just test it and see exactly what's going on with it. All right, this is a transistor that was getting warm, so I'll go ahead and remove the two screws, and because it's in a socket, it'll just unplug and then we can test it. So it's interesting to note these are all 2N3055 transistors, so they're super common. The 2N3055 is kind of the workhorse power transistor for general purpose applications. Just compare that to that DLP 130-15750A Dynaload that I have. That has some very unusual TRW transistors, and I have a TRW data book from back in the day, and it doesn't even list the model of transistor that other Dynaload uses. So sometimes TDI did use some very unusual components. I think they were custom made and custom spec'd for the application, but in this case the 2N3055, super common and easy to obtain. So it's kind of interesting to note that the 2N3055 was originally designed and produced by RCA back in the early 60s, and these are all RCA transistors in here. but the date code again looks like 86, so you know they're definitely not that original kind of production version, but they're still the RCA brand. And the 2N3055 is rated 60 volts collector to emitter, and in this Dynaload it's rated up to 50 volt input, so you know that's a perfectly acceptable rating. Doesn't have a lot of leeway, but it is, you know, perfectly fine because you're not going to go past that 60 volts. And the continuous collector current is rated up to 15 amps, but because you have all of these in parallel, they're all sharing the load, you know, current, so none of these is seeing anywhere near 15 amps of current. Even, you know, when it's drawing 60 amps, just take the 60 amps and divide it out by the 20 transistors. I should also add there's 2 of these transistors are the driver transistors, so there are 22 transistors and then 2 drivers, so the other 20 are doing the actual current handling. The drivers are, you know, are not handling that main load current. And then the 2N3055, it's rated up to 115 watts at 25 degrees Celsius, and then it gets derated, you know, as the temperature rises above 25 degrees Celsius. So my suspicion is that this one probably started to run hot and went into thermal runaway, would be the most likely scenario, and possibly what happened in the other one that was replaced as well. Let's go ahead and get this transistor removed here. Also, if you're working on these sockets and needle nose pliers on that, when you put the screws back into these sockets, what you want to do is, just demonstrate that now, you don't want to just take the screw and drive it in because the threads are quite coarse on these screws, and you don't want to cause the metal on the other side to cut new threads. So what you actually want to do is turn the screw backwards a little bit until you feel it pop down right there. So maybe you can kind of see that when I turn it like so. Pops down, then drive the screw in and it'll go in very easily. So keep that in mind when you replace the screws on many types of transistor sockets. So, because if you don't do that, you could end up cutting new threads in, and then the socket can be easily ruined. It'll strip the threads out. All right, so as I was mentioning, they're very coarse thread type screws. Kind of a sheet metal looking screw. Alright, so let's get this. You can probably hear the power supply still running, and it is connected, but the voltage is turned off right now. There's nothing, you know, everything's de-energized, of course. Alright, that unplugs. So you can see the pins right there. Inside, and markings on the other side right there. Blue dot, so they've all been marked for some reason, probably for the beta, the gain of the transistor. And actually, you know what I'm noticing? Look at how sparse the heatsink grease is on there, and also on the heatsink down here. There's almost no thermal compound, and I don't like that. That probably means that the rest of these transistors need to be removed, and then something needs to be done, either new insulators or, you know, new heatsink compound. That needs to be addressed. That may be why this ran so hot. There may have been insufficient thermal compound. In fact, around this area right here, you can almost see there's nothing, you know, the metal is just bare. It's very, very sparse, and that's not a good thing. It can cause either hot spots on the transistor, you know, because it isn't, you know, having a good thermal connection to the heatsink, or, you know, the whole transistor can just end up running very, very hot. So I wouldn't be surprised if that's what happened to that other transistor up in that other corner up there. Maybe it went into thermal runaway. If you're not familiar with transistors and what happens, when they get hotter and hotter, they'll conduct more and more. And the more they conduct, the more current they draw, the hotter they get, and it becomes an endless loop, basically. It's known as thermal runaway, and the transistor will quickly destroy itself. So it can happen in audio amplifiers and devices like this and so on. So let me just move this out of the way, and I'm going to grab my meter here, and let's take a reading on this transistor here. See the display there? Yep. So the collector is the case, and the emitter and the base leads are on the bottom. So emitter to base actually is okay. That's perfectly normal. So you can see in one direction, when I have the leads here, how it's the diode drop, perfectly normal. If I switch the polarity, that. See, it's an open circuit. So nothing wrong with the emitter to base junction. Now let's go to the collector here, like this. I'm just going to touch on the cap of the transistor right there. Uh-oh, there's a problem. Yep, right there. So there's no short over to the base, but the collector to emitter is a dead short. So I'm touching right here in the emitter lead, and the red test probe is touching the cap. And then if I reverse the polarity like so, the black lead there, and still a good connection there. Yep, look at that, it's a complete dead short. And the other terminal right there, we're getting, so collector to base, that looks okay. That's normal. So collector to base, I'm getting a reading there. Let me reverse the polarity here. And then that's normal. Yeah, so when I reverse the polarity, the collector to base junction is okay. So it's interesting, those junctions measure, but there's a short between the collector and the emitter, and that should be an open circuit no matter which direction you take the reading with the polarity of the test leads. So that transistor is definitely faulty. Now, with that out of the circuit, you can actually test the Dynaload. Let me put some voltage back onto it and see what happens. If it still draws excessive current, there's something else wrong. If it doesn't draw excessive current, we can actually try to run it under a light load without that transistor in place. And I'm just going to reach around over here to the power supply. I just turned it up. It's something probably around 12 volts or so right now. And it is not drawing excessive current. Perfect. So check this out. You can see the leads are still connected here. Put this on DC volts. And if we go like so, right here, grab my leads. So 11.8. I just turned up the power supply to a random value there, but you can see the input voltage 11.8 volts. And 11.8 volts going in, and again the power supply has no current draw whatsoever. And the circuit breaker is turned on, so yeah, that's perfectly fine. Excellent. So I think that's the problem. So now let me turn this back around and reposition things a little bit here, and let's turn the Dynaload on and see if it actually is able to control a load and vary the load current and so forth. So let's try that next. All right, let's see if the Dynaload works without that transistor that's shorted. So I still have the power supply connected on the test leads on the back, and you can see right now the voltmeter is actually indicating the voltmeter circuit is completely passive. It doesn't need any power from the control circuitry to make that meter read. I think the same with the amp meter as well. It's just reading off of that current shunt. So I have the power cord right here, the appropriate connector on the ends. Let's get this plugged in here. So, all right, controls are turned down and power on. So light came on, fans are running. Perfect. So far so good. The fans sound really good too. The motors aren't real noisy or anything. So now, let's see here, we'll leave the voltmeter on the 60 volts, but I'll put the range down on 18 amps. So that should be perfectly fine. This is on 0 to 10. So let me start to increase this. Hey, look at that. Current draw is increasing. And let's go to 10 amps here. That's the full range on that 0 to 10 amp range, of course. Right there is maybe the maximum. So yep, that just turned all the way to its maximum. My power supply over there is indicating 10 amps. And let me get a better view of this meter. And it is showing about 9.5, it looks like. So very close. I would say the other power supply, yeah, it's just a little bit under 10. So actually if we turn this, oh sure, there it goes. If you turn the fine control up a little bit, and that moves just a little bit more. So if I go right there, that's 10 amps on the power supply. And yeah, perfect. Look at that. It's right at 10 amps on the meter. So it looks like the Dynaload is functioning. Now I don't want to run it too long with the covers off. Like I mentioned, there's absolutely no cooling going on in here because the fans are just blowing air and it's lost. It isn't actually going over the heatsink like it's supposed to. But it is working. So I'll go through and I'll check the pulse control and some of the other functions as well, but it looks like it's come back to life by removing that defective transistor. All right, let's take a quick look at the schematic for the Dynaload and see how the pass transistors function as well as the driver circuit. So starting over here, there's an integrated circuit that's marked as U1. It's a type 723. And incidentally, I noticed that the integrated circuit has a date code of the 3rd week of 1985. So again, it looks like this Dynaload was produced in the mid-1980s. And the output comes over here to these two transistors, and you can see the bases are connected together, the collectors are tied together, and the emitters are tied together, so they're just operating in parallel. Now up here is a note, and it says Q101 through Q122 are all 2 on 3055, so 22 transistors in total. So those are all the transistors that are on those heat sinks. So this is Q101 and Q102, and then the rest of the transistors are all the pass transistors. These two are just the drivers. So these are driving the base of all of these transistors, and you can see off of the emitter, it comes over here to the base of this transistor, it comes over here to the base of this transistor. There's a little wiggly line right there, just means this is repeated over and over again. And down here are the emitter resistors, so you can see off the emitter, it comes down, there's a very low value 0.1 ohm resistor. So if you don't have emitter resistors and you have all these parallel transistors, you'll quickly find that one of the transistors starts to hog all the current, and it gets hotter and hotter and ends up going into thermal runaway. So very straightforward circuit, and I think the best way to do this repair is going to be to just take the two transistors that are over here in the driver circuit and move them over to the failed transistor position and also that other replaced transistor. It'll get a matched set of transistors in the heavy current handling area that is doing the most work. So they'll be well matched, and I think that would have the best chance for the longevity of the repair and have the Dynaload work correctly. And then on the two driver transistors, I'll order up the new 2 on 3055s, and I'll get maybe 6 of them. And then I'll match out of those 6 the 2 closest and use those as these 2 drivers, and I think that would work perfectly fine. So if these are matched at a higher or lower gain than the rest of these, it won't matter at all. I'm also going to replace all the electrolytic capacitors that are in the Dynaload. There's not that many. There's a couple on the main circuit board, and there's a handful of them over on that other circuit board with that Burr Brown 3650. That isolation amplifier, and I really don't want that isolation amplifier being fried because of a faulty capacitor in its power supply. So again, the fact that this was manufactured in the mid-1980s, these capacitors definitely should be upgraded and replaced. So I'll go ahead and do that as well. So I'll get all the components ordered up, and then I'll continue on when they're here. All right, all the new components have arrived from Mouser Electronics. Now, Mouser is in no way a sponsor of the video. It's just one of the companies that I prefer to use when sourcing electronic components, but I also use DigiKey, and there's other numerous reputable vendors out there too. But no matter who you use, just be aware of fake components on the market, and there are a lot of fakes floating around out there these days. So companies like Mouser and DigiKey have very strict quality assurance programs so that, for example, when you buy these 2 on 3055 transistors, these are made by On Semiconductor, very, very high quality, but you can be assured that they are in fact a genuine On Semiconductor part. And these capacitors are made by Vishay, again, very high quality. Now, what I've decided to do, remember there are 22 of those 2 on 3055 transistors that are in the Dynaload, and I'm going to replace all of the insulators between the transistor and the heatsink. So I'm going to replace them with these greaseless type pads. So these are thermally conductive, but they're electrically insulating. And I'll put the part number up on the screen, so if you're interested and need to purchase some, you'll have that reference for that part number. So they work very, very well. Again, you don't need to use any thermal compound, so I'll clean off all the old compound that's on the heat sinks and on the transistors. And then what I like about these is that because there's no thermal compound, when you have a thermal compound, it always spreads out a little bit from the sides of the transistor and kind of creeps out over time. But in a device like this Dynaload, there's fans that are blowing air over the heat sinks, and that thermal compound becomes a dust magnet, and a major lint magnet really builds up over time. So you don't have that issue when you use these greaseless pads. They work very, very well. I've used them numerous times in the past, and of course they're very easy to install as well because you're not messing with that thermal compound. So I'll get started installing all of this, and I'll show you the update when I have the measurements on those transistors as well, because I'm going to pick the 2 closest matched and they'll become the driver transistors. So I'll show you the measurements that I come up with when I measure those. All right, I tested the 6 new transistors on my transistor tester, and you can see the HFE values that were measured. So this one at 238, this one 240. These are very closely matched, so they'll work very well together. Now these HFE values are much higher than what's shown on the datasheet for the 2N3055, but that's to be expected because on the datasheet the HFE measurement is taken with several amps of current through the transistor, but on my transistor tester it only uses a few milliamps of current for the test, and when you use such a low current the HFE figure rises up, so these values certainly do make sense. Alright, so I've removed all 22 transistors and cleaned the thermal compound off each transistor as well as the heat sinks, and it was pretty sparse. None of the transistors had all that much thermal compound, so I'm sure that's why that one transistor failed. It just overheated, and that transistor that we saw that was previously replaced probably had the same issue going on. So on the contacts for the sockets on each transistor, I just gently squeezed the contacts together. Some of them seemed like they were spread out just a little bit and weren't making very good connection, so that's been taken care of. And all the old mica insulators have been discarded, and I replaced them with those new greaseless thermal pads. So all the transistors are mounted, looking very good at this point. So this transistor right here and this transistor here are the two driver transistors. You can see one is on this heatsink, and then this is divided. This is a separate heatsink over here. And that's a good design because this will be influenced by the heat on this heatsink. This one would be influenced by the heat over here on this other heatsink. So as these heat up, they'll conduct more and more, and they drive the other transistors harder and harder, but the control electronics will compensate for that, so it will prevent it from going into thermal runaway. So you wouldn't want the two driver transistors, say, over in this corner here with no compensation going on the other heatsink. So I tested all the remaining original transistors, and they all test perfectly fine, and they seem to be matched. The readings are very close on all of them. So it's all looking very good at this point, and also that replaced transistor did test okay. So I went ahead and just kept it. It's in my spare parts bin. So of all the transistors, there was actually only the one that was actually bad. And I replaced all the electrolytic capacitors, so there weren't that many, but this board right here, these two in the power supply section. So the board's looking very good, no problems there. And on the little isolation amplifier circuit board right here, so there are 4 electrolytics. So that's all been taken care of. So I'll go ahead and continue with the reassembly, and when it's all back together, we'll be able to test it. Alright, before I put the covers on the Dynaload and test it under a heavier load, I want to make sure that none of the transistors is running unusually hot, meaning that it's hogging too much current. They should all feel about the same temperature, and we won't be able to test that when the bottom cover is in place. So right now I have a 5-volt supply connected to the Dynaload, and the Dynaload is drawing 10 amps. So you can see on this clamp meter right here, a little over 10 amps, about 10.6. Alright, so if I just go through and I feel the temperature of the transistor cases, they're all feeling equal in temperature. The driver actually feels just a little cooler, which is normal. Driver there, yep, a little cooler. Yeah, so they're all feeling equal in temperature, so that's a very good sign. It looks like the current is being divided amongst all the transistors evenly. So I'll continue with the reassembly of the covers, and then we can do one final test on the Dynaload and make sure that it's functioning correctly under a heavier load. Alright, let's check out the Dynaload and see if it's functioning correctly. So I have it connected to my 25 volt 50 amp power supply, but if I draw 40 amps at 25 volts, that'll be 1,000 watts. So you can see on that digital multimeter right there, it says 25 volts, so the power supply is already turned on, and that digital multimeter is connected to the front panel binding posts. It's just some wires that run right around there, and those binding posts are connected as a pass-through, to the back panel terminals, and that's where the heavy gauge cable is actually attached. So if you see up there in the corner of the frame, that very heavy gauge cable, the red wire, and there's a black cable that comes right around the corner right there. So those are leading down to the power supply. So the clamp meter right there will show the current draw, and that current draw should match this meter right here, and then the voltmeter here, when I turn the circuit breaker on, should of course match the digital multimeter that's showing the voltage. Now there'll be some voltage drop in the cables, so it'll be normal when it starts to draw heavy current to see that voltage drop down. That's not the power supply voltage dropping because it is a regulated supply. It'll hold at 25 volts. And then the wire that you see running right there is going to another power supply, and then I'll use that to test the external modulation input, and we'll do that as a final test. So that power supply is not even turned on right now. Okay, so let's power up the Dynaload. So fans turn on. I don't know if you can hear the fans because the noise reduction on the microphone may be blocking them out. And turn the circuit breaker on. Perfect. So that comes up 25 volts right there. So I'll start on the constant resistance mode. So this is 1 amp per volt. And what I'll do is I'll drop this down to a lower range, and then if I increase this, perfect, so it has some current draw there. So this is on 18 amps, so it's on the bottom scale on that meter. So we're drawing about 3 amps, 3 1/3 amps right there, go up to about 10 amps. This is very close to 10 amps, so we can see that on the clamp meter as well. All the way over to full scale, so we're 18 amps full scale. We can see that on the clamp meter, no problems there. And that tops out, if I turn that all the way up, so 26 amps. Perfect. So drop that back down. So if I go to the 10 amps per volt now, it'll increase faster. Goes up very quickly there, which is normal. And there's 40 amps, 42 amps right there, so that's 1,000 watts. Can go a little bit higher because the voltage dropped down 23 volts. Some loss in the cable there, but no problems. It definitely draws heavy current with ease. So that's looking very good. So now let's put this back to the 18 amp range, and I'll go to the 0 to 10 amps. This is a constant current mode. So in the constant current mode, if the voltage were to fluctuate from the power supply, it would still draw the same amount of current, where over here in the constant resistance mode, whatever you have it set at, it acts like a resistor, and if the power supply voltage drops, then the current would drop down. If the voltage rises, the current would rise up. Okay, so 0 to 10 amps. This should go to 10 amps full scale. Turn this all the way up. And yes, it does. Just shy of 11 amps actually. No problems there though. That's fine. 60 amp range, and then 0 to 60 amps. So we should be able to take this up to 40 amps. There it is, 42 amps. 40 amps right there. No problems whatsoever. I don't want to hold it there too long because I don't want to blow a fuse or a breaker on the workbench. I've got a number of other devices that are running, and that's drawing 1,000 watts. So and a little bit over that because there's some losses in the power supply too. But yeah, that's working very well, no problems there. Now the 0 to 50 volt range, like I mentioned, it acts like a power zener. I can't do that test because I don't have any current limiting, and if you use this mode and then you hit that voltage set point, it would draw extremely heavy current, so we don't want to do that. But the external modulation, so I'll leave this turned down, put this 60 amp, I'll go actually back down to the 18 amp range. Power supply is turned off up above, so that's fine, so I'll go to external modulation. And if I come up here, and I will turn this power supply up to just a half a volt. Okay, so it's at half a volt right now. And if I go here, I turn this all the way to full scale. Perfect. So a half a volt input is drawing 5 amps, and you can see that over on the clamp meter right there. So that's exactly what it should be. And if I go to 1 volt, so I'll leave this turned all the way up, and now I'll go to 1 volt input right there on the power supply, and it's drawing 10 amps. That's exactly how it's supposed to work. If I go to 1.5 volts, it should be 15 amps. Yes, it is. Looks very good. Let's see, this is indicating over there correctly. So it looks like the external modulation input is functioning correctly, and that's related to that Burr-Brown integrated circuit that we already looked at. That's part of that external modulation input, so it's nice to see that that's all functioning the way that it's supposed to. Oh, turn that back off again. Turn this back down. Set that back to 10 amps. Works very well, no problems whatsoever. So I'm really looking forward to using this Dynaload on my bench. I have a couple other electronic loads or Dynaloads, but I don't have any that go up to 1,000 watts. This is the largest that I have. Previously, the largest that I had was, and I still have it of course, but it's 800 watts. And then the 750 watt that I already mentioned, I have a small 100 watt, and I have an AC/DC EL300, which is a 300 watt electronic load. So I have a variety of different ones. They have different features, and they're all very useful, and I use all of them. But this one goes to 1,000 watts, and that's why I was interested in this model, because of its capability to go to that higher power level. So again, it's functioning very well. I'll go through the calibration on it and just make sure that the meters are 100% accurate, although it looks like they are, and just to make sure that the overpower protection and all the features like that are functioning correctly. And I'll check the pulse input as well, or the pulse generator. I'll double check that, but I need to make some other connections to some equipment just to monitor those pulses. But if I find that there is a problem with that, I'll revisit this and I'll share that with all of you if there's any further troubleshooting. But right now it looks like everything is functioning the way that it's supposed to. So very happy with how this turned out. So if you enjoyed this video, please give it a thumbs up, and if you're enjoying the videos on this channel, please remember to subscribe. There'll be many more videos coming up in the near future. So as always, thank you for watching, and until next time, take care. Goodbye for now.